Well, great. This talk may be a little bit different from the others that you've heard today, because I'm an industry guy, right? I consider myself an entrepreneur. It seemed like yesterday I was sitting up here in your seats, and then all of a sudden 30 years goes by and you're an old guy at the front of the room. So be careful. That's going to happen quicker than you think. So to make this a little bit more interesting, I can apply it to you. Who are you people and what do you want to do? Computer scientists, or like what are you guys doing?
Yeah, I'm animation.
Okay.
Computer science.
Computer science?
Yeah.
Okay, awesome.
Computer science.
Computer science?
Bioinformatics.
Awesome. Bio?
The
whole room of bioinformatics? Okay, over here? Okay, great. And up top? Okay, great. So I computer science guy, worked for Intel paid me to go back and get my MBA, and then became a business guy. So I have been building and growing companies since, I left Intel in 2003. So I'm going to tell you a little bit today about TechSite and apply that to digital pathology. And if you have any interest in building a company, I'll sort of take you through a journey on how that happens. Okay, does that get us there? Okay, so I'm going to take you on this journey. If you're an AI person right now, you got to do an AI picture, right? So that was generated by Dolly. This digital pathology thing, it's been a long journey. I've been doing this since 2006, since 2016. And I'm going to sort of take you on that journey today. I hope you notice the importance of workflow and the impact that AI can have. And then also I'm going to speculate a little bit on the future for you. Okay. TechSite is a company. We came out of the University of Utah, and we started in 2013. I came in 2016. And what we've built is a scalable SaaS platform to basically take a medical technician or a veterinary technician through a test and generate a result. We started the company focusing on environmental and veterinary to get to human health. And the reason why is it's super hard to get things. As you saw, Dr. Hart, we work with Mail all the time. We know Dr. Hart, Dr. Hip. It's hard to get things actually deployed at an institution. So we started off in veterinary and environmental because it's less regulated and allows us to start generating revenue so that we can do more of the cool stuff. So we are a totally virtual company. We've got people all over the world, 147 of us now. And I'll talk about where the success has been and why. So where are we on the digital pathology journey? Have you guys ever seen a technology adoption life cycle like this? Okay, if you want to build a company, you got to be really aware of this. There's a great book called Crossing the Chasm. And you heard some things, I think, today from Dr. Pantanowicz. I don't know where he said we are. I have some opinions on that, and I've overlaid the hype cycle with the adoption life cycle, because what can happen is you can get you think you're going to be really successful and get in with early adopters, and then you hit this thing called the chasm. The chasm is where you run out of early adopters, and all of a sudden there's no one else to buy your technology, because the Mayos of the world, the UPMCs of the world, they only actually go forward when they see other people moving forward. So you can get stuck. So I would propose that digital pathology is very, very close, if not in the chasm. And there's a few reasons why. There's been at least $1 billion over the last at least 20 years, okay? And out of the couple billion slides that are produced every year around the world, I can only count up maybe 50 million a year getting digitized. So we're looking at very, very small amounts. So if we're 5% and you go back to that, it shows you we're still at the very beginning of this digital pathology thing. There are over 20 digital pathology platforms that are trying to win out there. The technology is rapidly changing. The expectations of AI, it's at an all-time high. And so you can tell by that peak of expectations, there's going to be a fall. Was working at Intel in 2000 when the tech bubble burst. You're probably all too young for that, but you get this huge, rise of expectations, and then it falls off. So there are standards emerging, but I think is a good thing. But there's going to be some carnage because out of those billions that were invested, not everyone has generated revenue because it's taken a long time to actually get deployed. So to get across the chasm, according to Crossing the Chasm and Gordon Moore, who wrote that, you need to do a bowling pin strategy, which means you've got to focus on an area and then go out from there and sort of knock down the bowling pins. So like I said, we started off in environmental. We did a mold test. Mold is made up of these very small 1 to 5 micron spores, and it's very, very difficult to tell the difference between an aspergillus and a basidiospore. So it really forced us to help our AI get really good, and it's totally unregulated. That led us to veterinary, where we've done fecal, digital cytology, blood cell differential, dermatology, and urinalysis. That gave us success. I'll tell you a little bit more about that in a second, to being able to then go to human clinical pathology, where we focused on liquids and cells. And then now we're focused with Mayo Clinic on anatomic pathology. So let's talk about AI creation. When we started off on this journey, it was, back in 2016, you just couldn't go read a book and learn how to do this. So we've done a lot of experimentation. And this is sort of the methodology that we go through. You've got your training data, and about 10% of that training data is used for the AI to learn, okay? I feel like that 10% is cheating, right? Because it's actually using data from the training to learn, so you can't trust it. So we put a line between that and what we called holdout data. Holdout data is where we spend a ton of time because it's the test by which your AI is going to be judged against. So you can't run the training data never sees the holdout data. But if you run the AI too many times on that holdout data, eventually you're tuning it to that. And if your holdout is not broad, then when you do your study, you won't have a generalized model, and it won't work. So we spend a lot of time in that holdout data, making sure that we've got enough strata that the model generalizes, that we know that we'll pass the study. So one of the things that I can still remember, one of the first, as we started building a platform, I was what they call a clicker. A clicker is someone who actually draws boxes around the objects of interest. And we didn't know how to even do that. We tried boxing it too small, big, and it ends up you've got to be about a pixel around the object that you care about, because we're going to feed those into then a CNN. And basically we're using an object, and most of the time we're using an object detection network that then creates the model that counts and classifies objects. We found that you needed to have an active learning process. When we first started off, we thought you just need tons and tons and tons of data, right? You've probably heard that. Well, it turns out that you don't need tons of data, you need the right data. So we're looking for the right things objects that will impact the model the most. So we spend a lot of time in this active learning where we have experts clean the data, we then train a model, we analyze that data, and then we send it through a finder run, which finds more objects. And if the AI gets it right, then that's good. If it doesn't, that's actually good as well, because then we can find out what didn't work, put that back into the model, and train again. And so we train models today. When you get a lot of data, you end up with, it's really hard to manage lots of data. For example, some of our models have tens to hundreds of thousands of images. Imagine trying to keep all of that data pristine. It's very, very difficult. So we created a thing called the cluster view. It's a 3D visualization that lets us see how the model is actually clustering and classifying each of the different objects. So this 3D, those colors we can actually manipulate them in 3D space. And then you can go in, and where there's overlap of colors, there's probably some data in there that is wrong. So you can actually select those colors where they overlap. it brings up on the right-hand side the actual images that were in that cluster, and you can either delete them, change them to a different class, etc. And so that's how we can rapidly create models. We've gone from a year and a half to create a model down to literally 4 months because of tools like this. We had to build all of the ability in the tool to prove that the models are getting better. So PR curves, confusion matrices, you've probably all seen those. But then we created, when you're dealing with lots of classes, one model we have for mold is 160 classes. When you have that many classes, it's really hard to tell if a model is actually the right model. So as we train, sometimes Aspergillus will do really good. Sometimes Basidios spores will do really good. And we had to come up with a model to say, what are the important classes, add a weight to that, and do a penalty reward matrix to eventually come up with a single score that says this is the best model. So this really helps us because it was so hard to compare model to model, and now we can just look at a final score. Okay, another tool that we built was the holdout comparison view. So remember back to that picture where I showed you the training data, the holdout data, and then the study data. The holdout data, this is the test. And so we've got a view in our system, and these are white blood cells, where after the model runs on the holdout, it tells you whether it got it right, whether it found something that it wasn't expecting, or if it got it wrong. And then the data manager can then, again, make changes to impact the model. So between the cluster view and the comparison view, this is where our data managers, and the data managers are basically the data scientists creating the model. This is where they spend a lot of their time. Okay, let's talk SporeSite. SporeSite was our first, if you think back to that bowling pin slide, SporeSite was our first attempt at doing really good UI and AI. So if you go and get your house or this building mold tested, they're going to run a little pump, and some mold and air stuff is going to come and impact a little gel slide that has mold on it. And if you then send it off to a lab, today they only read about 30% of the trace because it's too expensive to read the whole trace. It sort of looks like this. So they'll read about 30% of it. And if mold is on a portion of that slide that the actual tech is not reading, you actually get varying different results. So we didn't, one of the things that when you get into practical cases like this, you don't know if your AI is performing or if it's the tech that's performing or not, or the pathologist. In this case, it's a mold tech. So what we found, we actually developed this with one of the leading mold experts in the world. He lives in New York, and I got to go to spore camp where we tromp through the forest, find mold spores, and then put them on the slide. It was super fun. But he was getting super wild results he would read a slide, 2 weeks later, he'd read the same slide, 2 weeks later, he'd read the next slide, and he would get varying different results. We knew he was an expert, so why was he so different read to read? It turns out it was because of the method. Because they're only reading 30%, if there's spores in that area that they're not reading, they're going to get it wrong. So the AI, it reads the whole thing. So we created a test that is much better than the gold standard. So the next challenge that we faced in mold was, how do you actually get an image? If you take a mold trace, which is pretty sparse, right? These are microscopic little mold spores. If you put that on a whole slide scanner that was developed for tissue, it actually produces nothing. You get an image of nothing because the tissue is nice and flat, using microtome, and it's nice and flat and it's got lots to focus on. Well, on a spore slide, there's literally just microscopic things. So when the scanner goes through its focusing algorithms, it just gives up and produces a nothing image. So we had to go to the drawing board, and we actually created patented technology that we print fiducials, which is this little thing right here, on the slide or the cover slip. So we actually had to go to the UK. We found a company that would pad print ink on a cover slip, which is a pretty cool little robot that does that. And then we taught the scanners through an API to focus on the fiducials. And then we did studies to find out where the mold was at. And it turns out it's about 10 microns below the cover slip. So then we said, Scanner, I know that you don't think there's mold there. Trust us. Just find those fiducials and scan 10 microns below. And voila, you actually get images of the mold spores. So we've done that for vet fecal, which is just microscopic eggs that are floating in a solution that impact the cover slip. We've done it for vet urine. These are bacteriology slides for human. And then this is the mold slide. So those are basically cover slips or slides with fiducials printed on them. Okay, so this is our home inspector process. We had to, basically home inspectors go, they run that pump, they send it into our lab. When you think about workflow, we had to actually create an app because they were filling out paper to say, hey, I took this sample in the kitchen, I took this sample, in the basement. So we just gave them an app, again, to ease the workflow for everyone. And then we get the samples, we prepare them, we scan them, we upload them. And a test that used to take 15 minutes to do and create a report now takes 2 minutes. So this is what they end up looking at. This is what our software looks like. So the scan gets uploaded to basically to AWS. We run the GPUs, we run the AI, and then we present that in a workflow that you can get to through a web browser. And the technician just has to go say, verify that the AI got what it was supposed to get. And at the end of the day, you end up with a super simple, easy report that includes pictures of what's in your house. Now, I hate to say this, I had a flood in my house, and those are actually mold from my house. It was pretty gnarly. So yeah, if you have water problems, get a mold test because you don't want to be breathing that stuff. Okay, key learnings from mold. It was very hard for us, and it really pushed us as computer scientists to get our AI working better because these things are tiny, tiny, tiny circles. And to tell the difference between them was difficult. So we actually appreciate all that work that we did with mold because now we can do really good AI. As part of that process, the hyperparameter testing was very critical. And because you basically, you can't just predict what they're going to be. You actually just have to go run a bunch of tests. Scanning sparse samples, we talked about that. The workflow was critical. We tried to not stain slides, and it ended up that you have to just use the industry standard staining, which was it's basically a blue stain. There were opportunities to digitize other areas, the chain of custody and reporting, and then customers loved images in the reports, and that's actually paying off dividends that I'll tell you about here in a second. So super cool little project. We love it. It's fun, and we do about 2,000 samples a month. Okay, let's talk about vet. We partnered with Zoetis. Zoetis was Pfizer Animal Health. They went public a few years ago, and they're the largest pharma diagnostics and reference lab for pets in the world. Okay, so we worked on initially a fecal test, and we met them at a trade show where we sold them on the idea of taking this little scanner. It's called a Grundium from Finland. You take that scanner and you put a slide on it, and you end up with the results of a fecal test. Okay. Now, since we released the fecal test in 2020, we've done digital cytology, which means so there's literally 50 pathologists that are waiting for slides to come in from 40 different countries. We've built a blood differential, equine ovum parasites, dermatology, and just finished urinalysis. So basically, you create slides, you put them on that little scanner, it goes up to the cloud, we analyze it, and Zoetis basically takes that result and puts it in the medical record. So here's what fecal ovum parasites look like. If you had a dog or a cat, and they got sick, this is how they would get sick. These are little parasite eggs. These little ones right here, toxicars, they're like in playgrounds. These things will last forever. So be careful when you go to playgrounds. But the cool thing about this is our AI was proven at Oklahoma State University to be as good as a parasitologist at OSU and way better than normal vet techs. So Zoetis was super happy, and they rebranded our product to be VetScan Imagist, and it's now their product, and we just create it and create AI and workflow for them. This is the digital cytology for a virtual lab. So if your dog or cat has a lump or a bump, They'll stick a needle on it. They'll do a fine needle aspirate onto a slide. They'll scan that in. It comes to a virtual lab with 50 clinical pathologists. They'll look at it, and within an hour and a half, you'll get a result. So it used to cost about $144, and it would take a week. Now it's $69, and it takes an hour and a half. So a lot more dogs and pets are getting treated because of technology like this. We also do blood smears. So basically, you know, take the blood from a dog or a cat, you put it on that scanner, and we can tell, we'll basically count all the different types of white blood cells. Dermatology, these are generally from ears, and you're looking for yeast and bacteria. And then this is a urinalysis. Urinalysis is pretty cool because you get to see crystals and casts and fun things that are in the urine, and they can tell a lot of things about the health of the pet from their urine. Okay, what were the benefits from this? So Zoetis went out after we got this solution out there, and they did some market research, and these were the results from the clinics. It frees up their staff time, it sped up the results, the accuracy was way better, and they got better compliance with the meds. Think of Zoetis as a pharma company, so they want the pets to take the meds that they've developed. And so if they can identify the problem and have the meds right there in the office when you, instead of you have to sending it off to a lab and waiting for a week, if you can say, hey, your dog needs an parasitic medicine because it has parasites right there, then you get better compliance from the pet owner. Again, lots of different benefits to the practice, from freeing up their staff time to additional revenue and just better patient care. So we just find more things. Okay, key learnings from the vet market. Significant tooling was needed to create good AI and perform the clinical studies. So this is really where we honed and perfected that model of holdouts and how to generate good results. The other thing we learned in this one was slide staining and scanner diversity is key. So when you have, when you're trying to create a good model that generalizes, you got to make sure that it's across multiple scanners, multiple stains, or you can just hone in on, if you give AI a simple problem, it's going to come up with a simple answer. So give AI a hard problem, and it comes up. We like to think of AI as a super, super smart but lazy person. So you want to give it a hard problem. Okay. Lots of indications on one platform. It definitely increased efficiency and accuracy. And getting that data out to the practice management system is critical. So reporting is important. Okay. That led us to Mayo Clinic. Mayo Clinic, we just announced a partnership last year where we are building a digital pathology for both AP and CP. We're aligned with Mayo Clinic's vision, and just like we did on vet, we're now doing that on the human. Dr. Hip talked about the Mayo Clinic platform. They've got tons of data that then we can use to create multimodal AI. Here's what the platform looks like. You bring in images to an image management system. You've got that AI, you've got the workflow, you get reporting out, and we're going to start allowing third-party algorithms in the system. You guys need to go? That's okay. I understand. I'm standing between you and dinner. Okay, we work with a lot of different scanners. And Dr. Hart talked about the Pramana scanner. It is a total paradigm shift. And if you're going into digital pathology, I would definitely take a look at Pramana. Okay, these are the tests that we've created for the human market. Fecal ovum parasite. Basically, we find parasites that infect humans in the feces. We do that across both permanent mounts and wet mounts. And we've been doing that with ARUP since 2019. It's now deployed at Mayo and other big labs across the country. One of the key things that you've got to do is get journal articles. So we did publish with ARUP and Cleveland Clinic in JCM. And you can see some of the results. It tripled the capacity of what Mayo can do. and it increased their positivity rate and really speeds up those negative reviews from 3 to 5 minutes down to 30 seconds. We support a bunch of scanners, and that led to a project with Mayo on gram stains. Again, we do the same thing, stain in a gram slide, and then do a semi-quantitative score for grams. Similar process, scan it in. You can see how we're using those slides with the fiducials on them. Again, similar results in going from 107 seconds down to 26 seconds across multiple scanners. Automated blood differential, very, very similar to what we did in the vet market. We count and classify all the different white blood cells and red blood cells, and the technologist through the workflow confirms that they're right. If they're not, they can correct them right there. Again, multiple papers. It's as a vendor, you've got to have, third-party peer-reviewed articles so that you've got the credibility. So that people will adopt your solution. Again, across multiple scanners, which again makes it a pretty challenging problem. One of the coolest things that we've done recently is what we call TechSite SureView. We partnered with BD. BD is the #2 player in the world for cervical cytology. So this solution is now going to go to the world through BD as their cervical cytology solution. It's starting off in Europe, and then we'll come back to the United States once we have FDA clearances. On a pap smear, there's a circle on a slide that contains about 50,000 cells, and the AI counts and classifies all of the different type of atypical cells on that slide. Then it presents it in a way that the cytotech can mark the cells and then forward that on to a pathologist who's going to review it. We are doing a cool thing down in Puerto Rico that just started this week, where we're doing 100% QC review on all of their slides that they read manually today. And during this week, we've already found a couple patients that would have been missed by a manual review that were caught by the digital review. So literally a woman's life will be impacted because we were able to do, get better results. So just to give you a rough idea of what that looks like, at this lab down in Puerto Rico, that's about 2.9%, which if you were part of, if you knew someone that was in that 2.9%, that's a big deal. And then those are the scanners that we support. Bladder cancer, we partnered with an innovative company called CytoBay, and CytoBay has a unique technique to keep immunocytochemistry stained cells on so that you don't lose them during the staining process. So we basically the AI looks for brown cells in bladder screening, for bladder cancer screening. Okay, one last project that we're working on with Mayo is in the heme fish area. And with heme fish, you're looking for different types of leukemia. And you're doing that by how the fluorescent probes bind to certain DNA characteristics, and basically they fluoresce, and depending on the pattern, you can tell what type of cancer they have and what type of medicine would be most effective at treating it. Okay, so key learnings with that whole AI development for both environmental and pets applied to human. Very, very, very similar. And scanning remained one of the most challenging issues. Workflow, again, was so critical to improve efficiency, accuracy, and getting that data out to the LIS, which is Lab Information System. It takes a long time, but it also represents additional opportunity to provide additional ROI. Okay, that leads me to Dr. Hart touched on this, or Dr. Hip touched on this a little bit. We are helping Mayo go from Digital Pathology 1.0, which was an LIS-driven effort that started about 5 years ago for Mayo. They digitize all their slides today, but all that, they feel like a lot of what it is to increase their costs, but they weren't able to get a lot of the AI that they mentioned actually into clinical practice. So we're helping them build Digital Pathology 2.0, where it's basically creating a workspace for pathologists where they don't have to log into 7 applications. They just go to one application that is driven and developed specifically for the pathologist that allows homebrew AI, third-party AI, and the AI that we're creating with Mayo to be more readily accessible. So our vision for Fusion, which is the name of that platform, is to transform the global practice of pathology by unlocking the value of digitization in AI. Once you've got these slides digitized, you can get some of the cool things that Dr. Hip talked about. You just need the rails to be able to do that. So how do we do that? It goes back to the same thing that we learned in veterinary and environmental. Workflow, integrations, industry standards like DICOM will get that efficiency and accuracy that you need. So this is what we're building right now. This is sort of an eye chart, but it starts with scanning. It goes to infrastructure and how you store these things, how you get AI and third-party AI to run, and basically prioritize what the pathologists are working on so they're working on the right things. The end result, the benefit, improved patient care, better quality of life for the pathologists. They should be able to get a good ROI as well. And if we focus on bringing down the cost of digital pathology, then we'll be able to accelerate digital pathology adoption so that we can have a globally connected ecosystem. So where are we going? Phase 1 is generally digitize and automate an existing workflow. So I showed you basically lots of examples of that today. Phase 2, we're going to create AI that takes the result of the AI that we're running, compares it to the end result, and do what we call a phase 2 classifier, where we will be able to eliminate the need to look at a high percentage of negative samples. So with every prediction on an image that you get, we can then, if we compare that to the end result and run another model, we'll be able to predict and just eliminate, so you won't even have to look at a high percentage of the negative samples. That will also enable us to prioritize cases and order stains so that you can get this whole process done quicker. One really cool thing that's happened that the Googles and the Facebooks of the world are doing for us is they are getting to a thing called a foundation model. And a foundation model will help drive down the cost and the time required to create really good AI. And then, as Dr. Hip mentioned, you're eventually going to get to the place where it's not just image data and morphology, but you're going to be able to add patient history, genomic data, etc., and create multimodal AI that will get insights that we've just never really been able to see before. So with that, I hope you can get to dinner here soon. Any questions? Yeah.
Thank you for your presentation. It was really, really interesting. I have a question about 4+ labs. When you mentioned Puerto Rico, I remember they were the first laboratory to, at least in the Americas, implement the first treat. I think Galen for their prostate solution.
Yeah, from IBEX.
And from your perspective, does that influence the dynamic at all? Do you see them as a standout in any way? Because this is another kind of milestone.
So Mariano is the owner there, and he is just super visionary, and he's like, the future's coming, it's now, so we're going to implement it. So he bought 2 P1000s, which are really big scanners. They're about $350,000 a piece. So he bought 2 of those, and he went fully digital and implemented the IBEX product for prostate. And he just feels that this is a competitive advantage. And he can, look, he already impacted 1 life this week by giving a correct diagnosis where it would have been missed. So he's just super visionary. Any other questions? Yeah.
Thank you. A great presentation. Was there any difference in present level for the study of the human parasites and transferring the cancer?
Yeah, so there's a big difference. So for big labs in the United States, they can do something called an LDT, which is a lab developed test. So if they have a medical director they can implement something like the parasitology test, basically by doing a validation study at their lab. Small hospitals wouldn't be able to adopt our solution. We sell it as research use only until it gets FDA cleared. That's definitely different for cervical cytology and cancer. So with cervical cytology and cancer, all of the CLIA regulations actually exist because of cervical cytology. A senator's wife, unfortunately passed away due to a misdiagnosis. So when you're dealing with cancer, most labs are not willing to do that as a primary screening device until it gets FDA cleared. So we're in the process right now of going through the FDA clearance. And you've probably, if you've been watching this area, the FDA released a ruling that they're going to basically try to take lab developed tests away from labs and have everyone go through the FDA to get their tests cleared and approved. But yeah, it's definitely different depending if it's life-threatening versus, you've got a little diarrhea. Any other questions?
We had one online.
Okay.
Over here. Someone wants to know, can you clarify a bit more how AI is exactly used in this system?
Yeah. Basically, for all of those tests that we do, the AI is what predicts where the parasite is, where the blood cells are, what type of blood cells, finds the crystals, counts and classifies the crystals. So it is doing all of the work of finding the objects and either counting or classifying or giving a semi-quantitative score.
I guess that brings up my own question, which is, what kind of machine models underlie like AI?
Yeah, so it's object detection network. A lot of the times we're using YOLO. This is the underlying architecture.
One quick one.
Yeah.
So you mentioned the Pramana scanner with particular enthusiasm, and that was a paradigm shift. I was wondering what about it makes it unique.
Yeah, so Dr. Hip mentioned a few things. The ability for the scanner to do what's called a volumetric scan. When it does a scan, it gets all the Z-stacks as it's scanning. Now, the problem with that, if you kept all those Z-stacks, you would get a super large image, right? Bigger than what it is today. I mean, most of these images we're dealing with are 1 to 2 gigs. So if you kept 13 Z-stacks, you'd get 13x the size of those files. And that's just not practical or realistic. So what smart inline volumetric scanning does is it lets let's say for pap smears, it lets our pap smear algorithm run on the scanner attached computer. When it sees an abnormal cell, it will keep the Z-stacks around that cell and throw away the Z-stacks everywhere else. So we get a file that's about 1.2x the size of a normal file, but the cytotech gets to see up and down the Z-stack so they feel more confident in their call. So the ability to run our algorithm on the scanner so that we can impact this quality of that scan so that we can then see the different Z-stacks. That's a game changer. The other game changer is it's fed by a robotic arm so that you can have multiple scan heads, so you get throughput, redundancy improvements. And then Dr. Hip mentioned they have QC. So they basically have a blurry detector and other items that help us know if you got a good scan so that if you have to do a rescan. And they will do some things during that QC process that make it so you probably don't have to stick another slide in there. It'll just auto-correct it and put more focus points or something to try to improve that blurry area. So super cool technology. We've seen lots of changes in scanners over the years. That little scanner is amazing. It gets better than expected image results at 40x. But the Pramana is just a game changer for those respects. Good question. Okay, anything else? Well, I appreciate your time. And there's one more question. Okay.
How do you minimize the amount of false negatives
from the scanner? So the scanner is just giving us an image. right? So what we do with all those, with the printed cover slips and everything that we do to try to get good images, if we can get a good image, then it's our job as AI developers to basically train out the false negatives and the false positives. So there's lots of techniques to that, most of which we've just had to develop in-house. And I took you through that sort of that iterative training cycle. AI is really about data. And in our case, data are images. And so getting images, the right images in the training set to affect the model will then improve your false negatives, decrease your false positives, basically get your true positives to where they need to be. So it's a very manual process.